All right. Good morning, everyone. Welcome back to Math 154, Week 13, Lecture 12, Monday, April 18th. As always, going to talk about some due dates and then get into the new material, which will be 8.3 today. So previously assigned 6.2 homework and 8.1 homework due on the 18th and 20th, respectively, today being the 18th. The Excel 6.1 file, our next to last Excel file due, is the 18th. Video quiz 4, which will also be our next to last quiz. I said I might have two more. It's only going to be one more. So that's due the 18th. We will start and finish 8.3 today. Not a very long section. In fact, we'll get out a little early. And that'll be due in a week on the 25th. And then as the second reminder, your final exam will be Wednesday, the 27th. We will not hold class that day. You will just be taking that exam through my math lab like the midterm. So the final, unlike the midterm, is only one day. So make sure that you pay attention to those instructions. It's only Wednesday, the 27th. We won't hold class. There's no class after that. Make sure you take it at some point during that 24-hour period, whether it's during the exact class time, before, after, I don't care, as long as you get it done. If you miss it, you get a 0, and you don't want a 0 on the final. Nobody wants that. Of course, extenuating circumstances are extenuating circumstances. Email me, let me know, provide documentation, whatever we have to talk about, and we can figure something out from there. Now, your review materials for the final are going to be a little different, but also a little the same from the midterm. So the final exam is cumulative. So everything from chapter 0 all the way up to whatever we finish in chapter 9 is potentially on the final exam, but you will get reviews to narrow down what you should focus on. Now, the midterm, I gave you a set of 40 or 50 or 55, somewhere in that ballpark questions, and I provided a document in Canvas. I gave you the questions, I gave you the answers. You're responsible for all the in-between. You should still use that document to study for about half of the midterm. So the midterm is cumulative, and anything from the first 4 chapters, arguably 5, because chapter 0 is in there as well, you will study for that using the midterm review again. To study the new material, the stuff from chapter 5, 6, 8, and 9, I have provided a second review that's in Canvas, as well as an interactive review in my math lab, because I know the math can be a little more challenging for chapters 5 through 9. So I wanted to provide more like an assignment. It's not actually an assignment. It's not graded. If you don't do it, that's fine. If you do it, that's fine, whatever. But I do suggest doing it. So again, for the chapter 5 through 9 material, you do have something in my math lab. It has just been assigned this morning. If you go into your assignments, it is one of the first 3 things up there. It'll say chapter 5 through 8 or something like that, review for final. And again, does not count as a grade, but I do suggest that you complete it. If you prefer to have the review materials like for the midterm, where it's just a document with questions and answers, I provided that as well in Canvas in the same location where the midterm review was. Don't forget your formula sheet is also in that section. 2 formula sheets, in fact. You have your conversions formula sheet for the chapter 2 stuff. We had a couple of questions like that on the midterm. And then you have all those finance formulas, which we have seen several times already. We haven't gone over all of them, but you've seen the formula sheet itself. So make sure you have that ready. Remember, your formula sheets, you're not supposed to be adding anything to them. You're not allowed notes, you're not allowed books, but you are allowed calculators for this test. The final, like I said, is going to be cumulative, but it is going to be the same length and time as the midterm. So 20 questions, 2 hours. Make sure you show all your work, submit it in Canvas within 15 minutes. We talked about the formula sheet provided. Email me if you need any partial credit. Say, hey, Mr. Beckner, from your 8 a.m. I'm sorry, it's not 8 a.m. class. I don't have an 8 a.m. class. I'm from your 9 a.m. class or your 10:30 class, blah, 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 blah. Can you check out questions 2, 14, and 19? I think I deserve some partial credit on those. And I'll go and look at them and give you partial credit as needed if your work shows that you deserve it. Anything else I need to talk about? I think that's it. So after today, we only have 1 more week of lectures. I will most likely put up an additional video after we do the lecture a week from today. So you'll see me post the lecture from today, but then I'll also post a link to something I've previously recorded. It will be a final exam review. It's not cumulative. It will not cover everything in the hour and 15 minutes, however long that video I made was. But it will at least cover some questions. It's not a mandatory watch, but it's just something that I like to post in case anybody wants to see a little bit of material completed from the review by me. So yeah, again, after next week's lecture, when you go to the Canvas links, you'll find week 14, lecture 2, which will be chapter 9 material. And then below that, you'll see something that says final exam review, which again, I won't be doing live because we won't have time for it, but you will have that available if you have extra time to watch it. Okay, so with that being said, we can go ahead and get into today's material. We finished 8.1 last time. We're going to get into 8.3. We're going to talk about these R's and R squares, talking about how we can use some basic math. Well, not that basic. Getting the value of R and R squared is not that basic. That's the thing that we let Excel do for us. But once we have that value, the size of that number can tell us whether there's strong correlation or weak correlation, whether there's positive or negative correlation, those kinds of things. So let's go ahead and get it.
So 8.3, we're skipping 8.2. We go right to 8.3. And this is the last section of chapter 8. And this one will be quick. Correlation coefficient. This is that R squared we have been talking about constantly, except, well, R squared isn't the correlation coefficient. R is the correlation coefficient. R squared is called the coefficient of linear determination. I will admit I have swapped these names before in my head. The good thing is that doesn't really matter. It's knowing what R squared is and interpreting that is important. So I'm not going to give you a test question. What is the correlation coefficient? What is the coefficient of linear determination? The test questions would be, what is this value of R related to? What is this value of R squared related to? So I say here again, see text examples for random versus non-random data. We'll get into that after we go over the definition. And I won't actually do see text. I'm just going to make some images myself. So R is the correlation coefficient. R is between -1 and +1. And did I write it in interval notation later? I do not, so let me write it to the side. So -1 less than R less than 1. R squared, which is literally just take the value of R and square it, is the coefficient of linear determination. Now in Excel does not display R. It only displays R squared. Honestly, I really do not care about the R value. I care about the R squared value. There's only one thing that R can tell us that R squared can't, but if you have the picture in front of you, the graph itself can tell you the thing that R was going to tell you. So in my opinion, R is unnecessary as long as you have the picture. R squared and the picture give you everything you need. Now, when you square a number, the basics of math is when you square a negative, it becomes positive. If you square 1, you get 1. If you square 0, you get 0. If you square -1, you get 1. So this number originally being between -1 and 1, when you square it, it can only be between 0 and 1. So R we call the correlation coefficient. It's the namesake of the title section, but R squared is what we're going to be much more interested in moving forward. We'll study R squared, but R squared is what we care about. I've brought it up since chapter 5 for math's sake. So the coefficient of linear determination, and this coefficient of linear determination, we'll get a better statement about that very soon. So R squared is between 0 and 1. So R, an R value of -1 means there's a strong negative correlation. When I say negative or positive, what I'm talking about is the slope of the data. So if your data does something like, why do I keep drawing all 4 quadrants? So if your data does this, whether it's really tight or really loose, this would be negative correlation. If your data looks like this, and again, no matter how tight or loose it is, if it's just trending upward, this would be positive correlation. So when we say negative correlation or positive correlation, we're talking about the line or curve of best fit would have a positive or negative slope. So if the R is negative, it means the slope of the line is negative. If the R is positive, it means the slope of the line is positive. That's a very easy thing to associate between them. The closer to 1 or negative 1, the stronger the correlation. So 0 means no correlation. So if you have something like this, it looks like the data is moving in an upward manner, but they're very far apart from each other. It seems like there's not a super strong pattern. So if I had a line of best fit in here like that, which I don't want to have the lines there permanently, but if that was the line of best fit, it doesn't look that great. And they're positive, so R is probably in the ballpark of, I don't know, maybe 0.5, 0.6, somewhere in that ballpark. Whereas if you had something like this is probably an R value of like 0.9, maybe 0.95 even. And I have a really bad judgment of R values, again, because we don't really care about the value of R. I care much more about R squared because it has a much more important connotation. All right, well, if you had them looking like this R value is probably going to be something like negative, I don't know, 0.95. And this R value, which seems to be all over the place, is probably about 0 because the line of best fit's not really going to predict anything. So again, the only real useful side of R is you get a sign, and that sign tells you the slope, whether it points up or points down as you move right. The 0.5, the 0.9, the 0.95, and the 0 don't tell me that well, actually, how well the data correlates. That I'm going to get this percentage statement, and these don't link to it. It's R squared that's linked to it. So R squared is the better value to use to describe weak or strong correlation. So what's the R squared? Again, it's between 0 and 1. So 0 still means there's weak or no correlation, or if it's like 0.1 or 0.2. The closer you are to 1, the more perfect the correlation is, or the stronger the correlation is. If it's 1, it's absolutely perfect. If it's 0.99, it's amazing but not quite perfect. If it's 0.97, that's amazing but still not perfect. If it's 0.8, I mean, it's okay. It's not perfect, but it's still good. Your ballpark. If it's 0.6, I wouldn't use that as a model. If it's 0.3, throw it in the garbage because it's absolute trash. Okay, so R squared being between 0 and 1, so your pictures. And let's just take this last one that was these last 4, not all of them, some of them. So something like, I need to zoom out. This. As an R squared, this would actually probably be in the ballpark of 0.4, maybe even 0.3. I'm going to go 0.4. This last one probably should have been a 0.6. Again, R is really tough to judge because when you square a decimal, these numbers get further and further apart. If you square 0.6, you get 0.36. So 0.6 sounds okay, but really, again, the R squared value is what is the number that we're supposed to go based off of. And I'm not telling you the why. It has to do with that sum of least squares math that we don't want to get into because it would take us months just to talk about it. So that's not a great correlation. It's weak correlation. But it doesn't tell me whether it's positive or negative because we're talking about R squared. R squared of, let's go with this one, something like that. This R squared is probably about 0.9, maybe 0.91. And again, don't take this 0.9 as super accurate. It might have been like 0.95, but that's pretty good because the data is pretty tight. This would be strong correlation. The R squared is not telling me that the slope is positive. third one, I got a little ridiculous on that other axis, looked more like this. This was very tight. So that R squared is probably like 0.98, which is very strong correlation. But I can't tell that it's a negative correlation based on the R squared. I have to look at the data and say, oh, that's a negative slope. That would be negative correlation. And then finally, just random points, whatever. This we said would be no correlation. So the R squared is probably like 0.01. No correlation at all. So that's us showing strong, weak, positive, negative correlations. And if you wanted to throw the positives and negatives in there, you can. So the first one would be a weak correlation, but positive. This one would also be positive. This one would be a very strong negative correlation. And I wouldn't say positive or negative if something's no correlation. So that gives us a better idea of what we've seen in the past when I've displayed these R squareds. All right. So when we were talking about slope, when we were talking about intercepts, we gave you sentences, these cookie cutter sentences that you could use to say, oh, the output is changing at a rate of 3 apples per 5 oranges, something like that. That was the slope statement. This statement gives us our correlation statement. This statement gives us our correlation. If you take the value of R squared and convert it to a percent, that's what this says. This thing that I have highlighted right here just says convert, why is that happening? R squared to a percent. Maybe if I click, there we go. So again, this right here, why does it do that? Those are the same thing. Saying to take your R squared value and multiply it by 100%, that's just moving the decimal right twice. That's all we're doing. I said, yeah, right twice. That gives us the percentage of correlation. So if you have an R squared of 0.4, that means there's 40% correlation between these two things. If you have an R squared of 0.91, that means there's a 91% correlation, which means if one thing changes, you'll be able to predict that with 91% accuracy, basically, in the other thing. And again, it doesn't mean causation, it's just correlation. So if you have an R squared of 0.98, that says that 98% of the change in the output is because the input is changing. And say caused. Well, I guess because that's kind of a weak word to use. Because the input is changing, the output is also changing based on observation. That's a better statement to say. So here's our sentence, and this R squared times 100%. Again, this right here is just you writing the R squared as a percentage. So using the numbers above, you would say 40% of the variability, or 91% of the variability, or 98% of the variability, or 1% of the variability, which would be bad. So let's use the third one, 98%. So in this graph, 98% of the variability in the output can be attributed to the variability of the input. Variability means changing. So 98% of the change in the output can be attributed to the change in the input. I'm not saying it's caused by. I'm just saying there's a link between them. There's a correlation between them. So again, using the third one, 98% of the variability in the output can be attributed to the variability in the input. The changing output is linked to the changing input at a 98% effective rate, basically. So let's go back to our textbook. And let's look at our gas versus oil prices. We had an R squared up there. They gave us an equation. They didn't really point out the equation, but this 1.07, this is our fixed cost. The 0.02, this is our variable cost. So basically what we're saying is every time the price per barrel goes up $1, gasoline goes up about 2.5 cents at the pump per gallon. The 1.07 says, all right, if oil was free, gasoline's still going to cost you about $1.07 due to taxes, paying employees, paying for rent in buildings, digging holes, equipment, et cetera, et cetera. But really what we're focused on is the R squared. We said this line fits those data points really, really well. There's only a very small section that it's kind of off. And because these are chunked so well together, the rest of them, the R squared was awesome. It's 96%. Let's just call it round as to the nearest whole percentage. If you move it right twice, you get 96.38%. So that's a 96%. This says that 96, let's go back to our statement and just hold on to that 96% number. 96% of the variability in the, now what was the output? That was the gasoline price. Can I do this? That didn't work. Oh, no, not that, darn it, hit the wrong thing. Sorry, I gotta zoom out some so you can see everything. There we go. So again, the statement we make is 96% of the variability in the, instead of saying output, we would say gas price or price per gallon. So 96% of the variability of gas price can be attributed to or is linked to the variability in the oil price. So 96% of the change in gasoline price is linked to the change in oil price. That's the correlation. Gasoline prices at the pump have a 96% correlation with oil prices. Now, again, that's not demanding causation. Yes, there is causation here, but that's not the point of a homework or test problem with this. We will get into a couple causation problems with their multiple choice. Again, causation is really, really difficult to prove in the real world. So in other words, if oil price goes up $1, gasoline price is going to go up about 2.5 cents on a 96% probability, basically. Now what that means is maybe it doesn't go up exactly 2.5 cents. Maybe it goes up 2.4 cents. Maybe it goes up 2.6 cents. Maybe it doesn't go up at all. Maybe there's some weird fluke. But 96% of the time, if you increase the oil price by $1, you're going to see the gas price go up in the margin of 2.5 cents. Again, sometimes it's a little more than 2.5 cents. Sometimes it's pretty much dead on. Sometimes it's like 2.6 cents or 2.4 cents. It might be 3 cents, it might be 5 cents. It might be $1 because something really crazy is going on. But 96% of that correlation would be seen. This statement is super critical. Let's go back and have it all on the screen now. That statement is super, super critical. Very, 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 very critical. All right, what do we have? Time. Sorry, I'm looking for the assignment I want. It's 286. Okay. And that's it for the notes in 8.1 and 8.3. Pretty short sections in terms of notes. Let's go to the guided worksheets. This one on page 278. Please, on your own time, check this one out. This one's really, really cool. I want to give you the answers, but at the same time, I don't. Sorry, I'm thinking. I'm trying to compound how much time we have, how much I can do, whether I want y'all to I'm just going to go ahead and say the answers really, really quickly. So if you download this, it's much better than printing it on paper because then you'll have to type the link. So download the document, and then you can click these links, and it'll take you to a website. One or two of them, I think the links are dead now. They no longer work, so you wouldn't worry about that problem. But then they go on and show you a study with some data. Oh, no, I shouldn't have closed that. That's all right. That's all right. Download, assuming I haven't been booted yet. Perfect, because I'm probably getting booted in a couple minutes from my math lab. So this page, for each of the following situations, write down whether you think there's a true causal relationship or if there's just correlation, or if it's what we call spurious, which would mean no real relation at all. It's a coincidence. So shootings per day in a city versus the daily temperature in a city. And they go on to say that this is a possible causal relationship based on the data. And basically they say heat might make people irritable and cause shootings. So check out that information, see if you can maybe make that association. 2, divorce rates in Maine versus per capita consumption of margarine. Now, what is really interesting about this one, and the title of it actually gives you the freaking answer. U.S. spending on science, space, and technology versus suicides by hanging, strangulation, and suffocation. So this is something completely different, but look at how well these things correlate. They're moving and bending with each other, but do you really think these are linked to each other? No, this is what's known as spurious. It just happens to be there's a correlation. And look at the R squared. It's 0.9978. This is dang near perfect. But if you actually try and study a root effect, no. This thing is not causing that thing, or that thing is not causing this thing. Number of people who drowned by falling into a pool versus films Nicolas Cage appeared in. And we're not talking about the good films, we're not talking about the bad films, we're talking about all films. And look at how well these just happen to correlate. So some people spent a long time trying to find two things that have matching curves and then just slap them on top of each other. And these are two-way charts. You've got Nicolas Cage films labeled on the right, and that's the black curve, and then 120 drownings is here, 140 drownings is here. Why does this height represent the same height? We could stretch these or skew these and make it not look like correlation. But even though we make it not look like correlation, we still see a decent amount, an R squared of 0.66. That's okay. And that's because here it's going down, one thing's going down, the other's going up. They're kind of crisscrossing a little bit here and there, but there's still some correlation. But do you think that people drowning are causing Nicolas Cage to appear in films? Or do you think Nicolas Cage appearing in films is causing people to drown? No, that's not causal. That is spurious, S-P-U-R-I-O-U-S. And again, nope, that doesn't work. I'd have to hit back. The link that I clicked actually said spurious in the title. Per capita cheese consumption versus number of people who've died by becoming tangled in their bed sheets. First of all, I bet you're really surprised at how many people die by becoming tangled in their death sheets. Tangled in their death sheets. Hold on, that sounds terrible. Please don't sleep in death sheets. There's your problem. Tangled in their bed sheets. Amazing correlation, 95%. One's not causing the other. Divorce rate in Maine versus per capita consumption of margarine, 99% correlation. Look at how well these fit. Look at how well these ebb and flow together. But I can tell you that people aren't getting divorced because of increased or decreased margarine consumption. Sometimes data just looks the same. Age of Miss America correlating with murders by steam. How do you murder someone with steam? I shouldn't laugh at that. I'm sorry. I just don't understand how you murder someone with steam. I guess you lock them in a hot room. Hot vapors, hot objects. The other stuff I get. I mean, hot vapor is kind of the same thing. Very low numbers. When the first time I ever saw this, I saw the death by bed sheet. I was like, oh no, what's this gonna be? But it's very, very low. I mean, this is insanely low. So again, correlation. Correlation, not causation. Total revenue generated by arcades versus computer science doctorates awarded in the U.S. Now you might say, oh, well, this is both, no offense or anything, but nerdy stuff. No, computer science doctorates, nerds. People in arcades, nerds. First of all, I'm not trying to be mean. It's a blanket statement. Plenty of people go to arcades that aren't nerds. I'm not going to say anything about this one, and I'm not using that nerd in the negative connotation. Hello, math teacher. So, okay, yeah, there's correlation, but I don't think there's that many CS doctorates at arcades. I'm going to say this is mostly younger people, and you're not going to have a doctorate before you're 24 years old, roughly, on average. Again, there's what we call outliers, which that definition was on the previous screen. Outliers being data that just doesn't really seem to fit very well. 1 or 2 data points. All right, so you get the idea. There's lots of these. Check that website out. It's pretty cool. We're going to hit back. And there's a few more of these. So number 2 is spurious. Number 3, greenhouse gas emissions versus Arctic sea ice extent, which means how much ice there is. And that's definitely causal. Check it out. Density of yoga students versus yoga studios versus obesity rates. We would say that's possibly causal. So like the last one, causal, definitely. definitely. But this one I'm going to say possibly causal. And again, you can look at the data and you'll see some correlation. Then you just got to think, well, if you increase a number of yoga studios, should that drop the obesity rate? And that's why I say possibly causal, because yeah, if there's more workout places, there's more places that people can go to work out and maybe lose some weight. But you also got to consider economic factors. You also got to consider the density of the area. I'd say wealth is probably a bigger issue. Sale of winter boots at LL Bean in Freeport, Maine versus the sale of ice cream cones at the same store. Now, some people would say these two things have nothing to do with each other. I'm going to say it's causal, though. I'm going to say that one is affecting the other. And it's not that one is causing the other. There is a confounding factor causing both of them, and it's temperature. Not many people are buying ice cream when they're buying winter boots. Not many people are buying winter boots when they're buying ice cream. Now, yes, some people eat ice cream all winter long, nothing wrong with that, but we have massively increased ice consumption in the summertime. We have massively increased purchases of winter boots, the rate of winter boots purchases in the wintertime. So when winter boots are going to go up, ice cream sales are going to go down. And it's not people buying winter boots that causes the ice cream to go down. It's the temperature causing winter boot sales to increase and ice cream sales to decrease, or vice versa. So that's a confounding factor. Number of math PhDs awarded in a country based on average temperature. That's spurious. Average annual temperature by country versus average PSAT. They say possible causal because heat could lead to lower test scores because you can't concentrate because you're hot and sweaty. I would actually go against this in average annual temperature. I would actually link that more to an economic situation, because if your area can't afford AC for your school, it might not really have to do with how hot it is outside. Just your city has hotter schools because no AC. They are doing it by country, so it's a little more general at least. So that's why I still say possible causal. All right. Last thing I wanted to talk about, well, first of all, show you that definition that was on the screen, but I didn't talk about when it was on the screen. Outliers are data points that don't seem to match the others very well. So let's say you got a graph that looks like this. And then and maybe So these points right here fit the mold really, really, really well, no matter what we're talking about. But this point right here and this point right here, they just seem to be out in left field and la la land doing their own thing. Those would be outliers. They don't fit the mold. A lot of the times when people do studies, they'll completely exclude outliers. Now, they may exclude some, they may exclude all, they may include all, they may include none. It's variable depending on what people want to do with their study. Outliers can be an important thing to consider in your data, because you might think something is a perfect model when in fact it's not perfect. It could be really, 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 really accurate, but because these outliers pop up, that means the model isn't perfect. Sometimes just random things happen. And again, we're talking about people, and we're talking about health, and we're talking about finances, and we're talking about life expectancies. There's outliers. There's always outliers. When we talk about the average salary of a person, kind of a random thing to throw out here. I'll put it above the graph just because of that. Average salary of a U.S. person is somewhere in the ballpark of I think it's like $75,000. Let's just say it's $75,000. And you might go, holy cow, how is the average person making $75,000? That's because this is a mean. This is literally an average of adding up every single person who makes money and the people that don't make money, dividing by the number of people, and that's what we get, $75,000. This has tons of outliers, mainly rich people, the people that are making billions of dollars every year. These people make so much money that they throw off the average, I can spell average significantly. Some studies exclude the top 1%, possibly bottom 1% as well, to make equal cuts, to get a more relevant average, maybe in the 45 to 50 ballpark. Alternatively, some studies use the median instead, middle value. So if you lined up all 300 million American salaries from lowest to largest, from $0, because there are people making nothing, to, geez, what's Elon Musk making now? I don't even know. It's either Elon Musk or Warren Buffett. They're one of the top two or three. So whatever their annual salary is right now. So if you line all of them up and you pointed at the smallest one and the largest one, and then you moved closer to the middle. So the next, on the left, the next person who makes a little more money, which is still gonna be $0. And then on the high end, you move down to the second most wealthy person of the year. As you keep doing that, eventually you hit the middle person, somewhere around the 150 millionth person in terms of the middle. And then you say that is our average salary. Now, when you do that, that's another way of kind of ignoring the top 1% as a major effect. So when you think of a median, those top 1%ers, as you move from person to person to person, they have the same effect as moving from a person to person to person, making $40,000 to $40,001 to $40,002, which there are way more. And the median is in the ballpark of, I want to say 40K. I'm not going to take the time to look up these numbers since we only have a couple minutes left. But those numbers are in your textbook or worksheets at some point. We have mentioned them in the past. So again, a lot of statistics have outliers. Whether we use the outliers or not depends on the point of the problem. We may not be allowed to exclude outliers. We may have to have them depending on the study. We may want to use them to show, I mean, it ain't perfect. Maybe we want to use them to make people think that it is perfect. So you just throw data away. That sounds like a great idea, right? I think that's going to be good. I wanted to at least show a couple of the guided worksheet activities, just at face value. I'm trying to get to the end point of the course that I want to be, so I have been skipping some guided activities here and there just to get you your information. So here's a graph with a mediocre correlation. So about 60% of the change in minimum wage can be attributed to the change in the percentage of hourly paid workers at or below prevailing federal minimum wage. So what's interesting about this problem is that it feels like the higher the minimum wage, the worse off we are. This is more because minimum wage keeps going up over time, but not quite enough to really have a sustainable income, a livable wage, that is. But that's only a 60% correlation. That's good, but it's not great. And you can see the good, not great aspect of this. Here's one dealing with humidity versus temperature. So typically, the hotter it is, the more humid it is, but this is not true. And I really hope that they did this study in one region, because if you compared, say, the Virginia Beach or just Hampton Roads region to, say, the middle of or the southern part of Arizona, Arizona might be 100 degrees and have a humidity of 2%, whereas we might be 90 degrees and have a humidity of 100%, like all of last week. Good Lord. But if you just look at one region, its humidity index, which is a percentage of water content in the air, versus the heat index, which heat index is the temperature felt. And I'm sorry, that's what it is. It's heat index, not actual temperature. You can see up at the top, it says actual temperature. That does enable it to look across all regions. I'm trying to go too fast, so I missed a piece of information. I have to pay attention. Okay, so heat index. The hotter it feels, the more humid it generally is. The hotter it feels, the more humid it generally is. So if it's 80 degrees with a super low humidity, it probably feels like about 80. But if it's 80 degrees and there's a super high humidity, that's when it starts feeling like 90 degrees. So this accounts for Virginia, this accounts for Arizona. You don't have to go to a region. And this has a 98% coefficient of linear determination, a 98% R squared, which means 98% of this correlation, or of the correlation is up to 98%, excuse me, 98% of the change in heat index correlates to the change in the humidity, the relative humidity. Here's that gas versus oil prices again. We've already talked about that. Here's another one dealing with index of exposure to plutonium versus cancer deaths per 100,000 people. And we see that it seems to be increasing. We don't really have a gauge of what index of exposure means. We're not studying this. But these are a scary amount of deaths per 100,000 people. It's not super high, but you don't want to see any of them. And there's an 85% correlation. So it seems like plutonium causes cancer. But again, I'm not saying it causes it. It seems like it. There's definite correlation. We'd have to do some science to get the causation. Here is a chart of the miles from Albany, New York, to the price of a toll. And somehow this has absolute perfect correlation. I feel like these numbers were probably fudged, or that the concept is something a little different. So this is different tolls. I just don't feel like these tolls would correlate so perfectly. So I don't know if this data was fudged or if it's real. There are tolls or fees you can pay on things based on how far you go. Like if you go to DC, the last time I went 10 years ago, how far you go on the subway determines how much you pay. At least it did 10 years ago. Now, I know that other cities like New York, it's just a flat fee. But anyways, this is perfect correlation on what your teacher suspects is made up data, but he has not confirmed that. It just seems like the further away you are from Albany, the more you're paying in tolls. I'm going to guess they probably started heading towards New York City. I don't know. I just know there's expensive tolls that way. Per capita, here's the chart for consumption of margarine versus divorce rate with that 98% correlation that we saw earlier. Look how close those dots are to the line. But again, that's correlation, not causation. Finally, the one I wanted to show, I'll look at this one. Now, all these dots do seem to be going in a positive manner. They do seem to be going positive slope, but they're all over the place. This line is not near the majority of them. Look at that terrible R squared, 13%. This is actually a really fascinating one. It shows that the predictability of winning or losing is not really correlated to a strength of schedule, which is basically putting a number 1 team against a number 64 team, a number 2 team against a number 63 team, seeding, if you will. And then the R squared does not just deal with linear trend lines, it also does with exponential trend lines. This is an exponential decay trend line. So this was people trying to memorize a string of letters. Like if I said memorize QRZT, you go QRZT. That was easy. 4, I can do that. But if I said memorize QRZTAC, that might be a little harder, but most of you could still probably do it, 100%, QRZTAC. as I say, QRZTACB, maybe a little less memorize it. QRZTACBD. I'm just keeping this easy for myself. A little few memorize it. But then between 9 and 10, all of a sudden, this gets really hard. And we go from about 60% of people being able to remember it to about 20% of people being able to remember it. There's a drastic jump. And it's not like all of a sudden people have an easier time remembering it, which is why they don't do a linear trend line for this. They actually do an exponential because of that drastic jump. Drastic changes, we tend to see exponential models. But even then, it doesn't look like it fits that well. But in actuality, because it predicts these later three pretty well and at least one before, this R squared is 88%. 88% of the correlation of people being, 88% of people being able to remember these is correlated to the length of string of letters, or is attributed to. Now, first of all, this curve sucks any sooner than 7 because you can only have 100% of people memorizing things. So this curve is just complete trash before 7 letters. And then it's okay after. It's not so great for 8 or 9, but it's definitely going to be good for 13, 14, 15, 16, 17, 18, 19 letters, in which those numbers are going to be ridiculously low. So even though you might say, if you try to guess the R squared here, I'd probably guess it in like the 75 region, maybe 78 region. It's actually 88. There's a little more room, a little more wiggle room for the exponential models and small amount of data points. So when you start having tons of data points, that your R squared can get wacky. Or they're just all over the place with just a few data points. And do we have an exponential growth? I don't think we do. That's okay. This is all statistics. We don't need to do that. So bye-bye.
So like I said, we'll get out a little early today. I like to do all the chapter 9 stuff kind of together in 1 week. I don't really like starting it when we're in the middle of a chapter 8 material. So we'll just save it for next time. What do I want to say? What do I want to say? I mean, usual dates at the end, the stuff we've already seen. Today, 6.2 homework is due, Excel 6.1, video quiz 4. There will be one more Excel homework. There will be one more quiz. They will most likely be due on the 27th. Yes, 8.1 due on the 20th, 8.3 due on the 25th. Final exam is going to be the 27th. We talked about that earlier. We'll talk a little bit more about it next time or the time after that. As I said, I'll post an extra previously recorded video for you after we finish our last live to get together a week from today. And that's just going to be some final exam review questions where I actually show the coverage for them. Not everything, just some of them. But yeah, one more chapter's worth of material, one more week's worth of material, and we are done at the finish line. So keep it up. Keep looking at those notes to share in advance. Look at that chapter 9 stuff before you come to class next time. Get your homework done, start studying for the final. Make sure you know where all your materials are. Shoot me an email if you have any questions per usual. Besides that, have a good day. I know the weather's not going to be great today, so stay dry if you got to go outside, and we'll see some good weather a little bit later. All right, take care, everybody.